So I'm just going to go through a few examples of free body diagrams. I'm just going to talk you through as I draw some of the forces that are acting on these objects. In number one, we're talking about a water skier. And so you can draw directly onto the picture to see sort of what forces are acting on him. He's being pulled this way by the string, by the tension. Gravity is pulling him down. I'm just going to label this force of tension. This is going to be the force of gravity that pulls down on him. And then there's skis that are pushing up on him. Now, if you've ever, and that's our normal force, if you've ever water skied, there's one more force that we haven't taken into account, and that's the force of friction, or the resistive force acting on him by the water. And so if I'm going to draw a free body diagram of this, gravity always goes straight down. The force on the skier by the earth. And then this is sort of this way. I'm just going to draw the normal force a little bit at an angle because that's the way that it's sort of perpendicular to his skis. So this is going to be the force on the skier by the water. We have a force this way, the force on the skier by the rope, and then this friction force going backwards. This is the force on the skier by friction. I'm going to leave you to do number two yourself. Just thinking about the forces that are acting on this sled and kids. You have a tension force that's pulling on them. If the sled and the kids are one system, right, we don't care about just the kids or just the sled. So treat it as one body, or treat this as a crate. Treat it as a crate that's being pulled at an angle. You can make the decision whether there's friction or not. If you've ever been pulled on a sled, you probably know that there's a little bit of friction that's going to be pulling backwards on it. So there'll be some friction, there'll be some gravity, there'll be a normal force. So it's going to be sort of similar to number one. I'm going to do number three. Draw a force diagram for the table. So this is our table. This dancer is leaning over on the table, so they're actually pushing downward on the table at this angle. All right, so when I draw my free body diagram, I start with a dot, and the force of gravity is an arrow that goes straight down, the force on the table by the earth. And then this dancer is pushing sideways on the table, right? Pushing, and even though it's pushing this way, we draw the arrow coming out. So we push and draw that in the direction that the dancer is leaning on the table. So this is going to be the force on the table by the dancer. Now, there has to be some sort of friction on the table because otherwise the table would move and the dancer would fall. And so we have a force of friction that's going to go this way. Force on the table by friction. And then we have a normal force. Now, if I had a scale underneath this table and I was going to measure what the table weighed, or the force of gravity on the table, that actually gives us the normal force. And so if you push down on the scale, that normal force will get bigger. My normal force isn't going to be equal to this force of gravity, the force on the table by the earth. It's going to be equal to that plus the force on the table by the dancer. So it's going to be a tall normal force. Force on the table by, and let's call it the ground. So I think that you guys can probably do this one, number four, by yourselves. There's a rope over here. You could call this the right rope. And there's a rope over here that's pulling on the man. Call this the left rope. And so go ahead and just draw all of the forces and label them that are acting on the man. The question that I have, is there a normal force? And normal forces only appear when there are surfaces. And so this guy's not standing on anything. There are no walls. So there is no normal force. Um, I'm going to do number 6, and then you guys should be able to do number 5. So draw a force diagram for the skier who slides with negligible friction. So I'm going to say that we can ignore friction. So here's our dot to represent our skier. The force of gravity always goes straight down. The force on the skier by the earth. Now, the other force that we have is the normal force, and that comes from the surface at this angled perpendicular to the surface, and so the normal force will go this way. The force on the skier by the hill, we'll call it. Okay, so if there was friction, that friction would slow it down, or that friction would be in the opposite direction of motion, up. The friction would be pulling on the guy in the opposite direction of motion up the hill, but there is no friction. And so these are the only forces that we have. So when you think about the squirrel, the one thing, it's going to be a little bit backwards because the hill is in the different angle. All right. So this is just for the child. You're just going to draw it for the child. So think of all of the forces that are acting on the child. This guy's pulling here, and there's the rope, and there's the gravity. And I might say the child and the swing, so let's call that the whole body, so that include the swing in the child. All right. And this is sort of a weird picture, but we basically already had this with the rock. And so it looks like this, right? And then here is your um, object, right? So what forces are acting on it? And know this, on number 9, there are 2 surfaces. So you'll have 2 normal forces. All right, I'm going to have you guys skip number 10, and that'll do it for today.